All right, so today we're going to look at something you see every day, pushing, pulling, all kinds of motion, but through a completely new lens. We're talking about the physics of work and energy. Now, I know what you might be thinking. Sounds a little like high school science, right? But trust me, once you grasp this, it can totally change how you see the world around you. So let's just jump right in with a question.
Okay, so picture this. You're at the gym. You're holding a really heavy, say, 50-kilogram weight right over your head, and you just hold it there, perfectly still, for an entire hour. I mean, you'd be exhausted, right? Your muscles would be absolutely screaming. So my question to you is, was that hard work? Now, in everyday language, you'd say,
Of course it was. It was ridiculously hard work.
but, and here's the twist, in the very precise language of physics, you did absolutely zero work on that weight. None. And understanding that weird little paradox, well, that's the key to everything we're diving into today.
So to figure this out, we need to kind of shift our thinking. We need to adopt a whole new perspective, or as the lecturer in our source material calls it, a new Nazaria. This isn't about memorizing formulas, not at all. It's about learning a completely new way to look at and interpret the world. Okay, let's start with that word work. Because in physics, its meaning is super, super specific. And really, it all comes down to one simple thing: movement. So here's the deal in physics. Work only happens when a force makes something actually move. That movement, or what physicists call displacement, that's the magic ingredient. If you push on a wall with all your might, but the wall doesn't budge, guess what? You've done zero work. It really is that simple.
And we can actually break work down into 3 different flavors. First, you've got positive work. This is when your force speeds something up. Think about pushing a stalled car to get it rolling. That's positive work. Then there's negative work. This is when your force slows something down. Like hitting the brakes on that same car. And finally, there's zero work. This is when a force is acting, but it doesn't actually change the object's speed. A classic example is gravity pulling on a satellite in a perfectly circular orbit.
So this brings us right back to our big puzzle from the beginning. When you're standing there holding that heavy weight perfectly still, what's its displacement? It's zero, right? The weight isn't going anywhere. So even though you're sweating and your muscles are burning, the work you're doing on the weight, in the language of physics, is a big fat zero. And there's our aha moment.
Okay, so if work isn't just about how much effort you're putting in, then what is it about? Well, this is where things get really, really cool. Work is all about transferring energy. It's the bridge, the grand connection between applying a force and changing an object's energy. And the main type of energy we're talking about here, kind of the currency of this whole transaction, is called kinetic energy. It's a fancy term for a super simple idea: the energy of motion. If an object is moving, it has kinetic energy. The faster it's going or the heavier it is, the more kinetic energy it's got. Now, this leads us to what is basically the most important idea in this whole explainer. It's called the work energy theorem. And it's actually pretty straightforward. The total amount of work you do on an object is exactly equal to the change in its kinetic energy. They're like two sides of the same coin. Work is the cause, and the change in kinetic energy is the effect. This is like the fundamental rule for balancing the energy books in the universe. Let's make this real. Imagine that car again. When it's at a standstill, its kinetic energy is zero. Then the engine kicks in. It applies a force, moving the car, which means it's doing positive work. And what happens? The car starts moving. Its kinetic energy has gone from zero to something. That work that the engine did was literally transferred into the car as energy of motion. But it turns out not all forces are created equal. Some forces, and gravity is the perfect example, have this really special property. The work that's done against them can actually be, stored, and you can get it back later. This whole idea brings us to something called potential energy. So let's go back to our imagination for a second. You need to move a box from the floor up onto a high shelf. You could just lift it straight up, the shortest route, or you could meander around the room taking this long, zigzagging path to get to the same shelf. The question is, when we're just talking about the work you do against gravity, does the path you take actually matter? Well, for a force like gravity, the answer is no, it doesn't matter at all. The work you do against gravity is what we call path independent. All gravity cares about is the change in height, where you started and where you ended. But now think about a force like friction. For friction, the path matters a ton. If you drag that box along a longer path, you're going to lose way more energy to friction. And this difference is absolutely crucial. So these special forces like gravity, the ones that don't care about the path you take, they have a name: conservative forces. And here's the cool part: the work you do against them gets stored up as potential energy. So when you lift that book, you're doing work against gravity, and it's like you're compressing a spring. You're storing that energy, and it's just sitting there, waiting to be released. And this is where that famous formula, MGH, comes from. It's just a way to calculate that stored work, that gravitational potential energy. It depends on the object's mass, the strength of gravity, and how high up it is. And the second you let go of that object, all that stored potential energy immediately starts turning right back into kinetic energy as it falls. So you might be wondering, okay, why are we going through all of this? Why do physicists prefer to look at the world through this lens of work and energy? Well, honestly, because it's kind of like having a superpower. Seriously, thinking in terms of energy just makes incredibly complex problems simpler. You don't have to worry about tracking every little force and acceleration second by second. Nope, you can just look at the before state and the after state. It lets you totally ignore all the messy details in between. And this whole approach, this is what leads us to one of the most powerful and fundamental laws in all of physics: the conservation of energy.
But just before we wrap this up, there is one final kind of mind-bending twist that our source material brings up, and it really challenges everything we've just talked about.
Okay, so remember how we said work depends on displacement? Well, here's the thing. Displacement is relative. It completely depends on your point of view, what scientists call your frame of reference. The source gives this perfect example. Imagine a box sitting on the floor of an elevator that's going up. Now, if you're inside the elevator, from your perspective, the box isn't moving at all, right? So you'd say zero work is being done on it. But for someone watching from the ground floor, that box is clearly moving upwards. They would say that gravity is doing negative work on it. Two observers, same event, two different answers for the work done. And that leaves us with a really big, kind of provocative final thought. If two people can watch the exact same event and measure two completely different amounts of work being done, what does that even mean? If work is the transfer of energy, and that transfer depends on who's watching, does that mean energy itself isn't some absolute fixed thing? Could energy just be a matter of perspective? Definitely something to chew on.